so we're going to do two things tonight, I hope. I went through 3 lectures on the facts of life of reverse phase liquid chromatography, what you need to know to do it. What we're going to talk about tonight is why some of those facts are true. What is the mechanism of reverse phase LC? And there's a lot of stuff involved here that I hope you will appreciate being of a rather general nature. Not just chromatographic, but as a general nature, understanding mechanisms in chemistry in a general way. But I think reverse phase liquid chromatography is a sufficiently important topic, as are things related to it, that this is worth understanding. And then roughly half of the lecture will be on this, and then now it will be on an introduction to normal phase liquid chromatography, which is the exact opposite of reverse phase. Okay, so the two big issues in my opinion right now in terms of understanding reverse phase liquid chromatography is A, what makes it happen? What is the driving force for solutes to go from a polar eluent into a non-polar liquid? And there are basically 2 theories about this. And they're both old. Current theory is based upon what we call the hydrophobic effect. If you've never heard of the hydrophobic effect, I don't think you've ever had any biochemistry. And boiling that down to its essence, what it means is that the retention is driven by the dislike, the hatred of the solute for being in water. It wants to get out of the water. That's why it goes in the non-polar stationary phase. It doesn't like the non-polar stationary phase. It just hates water so much that it will do anything it can to get out of water. That's what the hydrophobic effect is all about. The other model is the exact opposite of that, and that is that the retention is driven by the attraction of the non-polar solute for the non-polar stationary phase, which is driven by the London dispersive types of interactions. You couldn't have 2 more different theories of what's going on here. So that's one aspect of what I mean by the mechanism of reverse phase liquid chromatography. The other aspect is this kind of chromatography a partition-like process, or is it an absorption-like process? And I'll define that with a cartoon very shortly. The conclusions, which I'm going to lead with, and you'll see hopefully why the conclusions are what they are, is that number 1, the free energy of retention of a CH2 group in reverse phase chromatography is predominantly driven by the lipophilic attraction of the CH2 groups in the nonpolar parts of the stationary phase for the nonpolar parts of the solute, and not by the so-called hydrophobic or solvophobic repulsion of the solute out of the mobile phase. The second part of the conclusions is that the nonpolar parts of the solute become embedded within the bonded stationary phase. That the nonpolar parts become surrounded by the C8 or C18 or phenyl group, whatever, that's on the stationary phase. Since we're talking about mechanism, I want to start with a definition of mechanism. I like the Webster New Collegiate Dictionary. It's only about that big, but you know, there's a lot of good stuff in it. And this is the definition of the word mechanism. The arrangement or relation of the parts of anything as adapted to produce an effect. That is the key idea of mechanism. That is, you arrange something so that it will produce a specific effect. That's what the mechanism is. Now, that's not normally what a chemist considers to be a mechanism. I think that this is a nice, simple chemical definition of a mechanism. It's the sequence of steps by which a chemical process takes place. I didn't say chemical reaction. A chemical process is broader than a reaction. We don't view, for instance, reverse phase chromatography as being a reaction. We think of it as a process. The transfer of something from a moving phase to a stationary phase. Here's an example of a real mechanism. The arrangement of parts to produce an effect. I'm betting that you guys are all way too young to ever have heard of Rube Goldberg. Anybody? Who?
They still have competition.
What?
They still have Rube Goldberg competition.
Oh, do they? Mm-hmm. Well, Rube Goldberg was a cartoonist. His stuff appeared in the newspapers in the 30s, the 40s, the 50s. I never saw an original Rube Goldberg, but one of my uncles loved to say, that's a real Rube Goldberg. That means that it's in a very unlikely way to do something. It's not the best way to do it. But this is a mechanism for causing this octopus to squeeze this orange to make your morning orange juice. I like this cartoon a lot because it comes from this book by Roald Hoffman. This is Hoffman of Woodward Hoffman of Nobel Prize. And he wrote a wonderful book. I like to reread it every couple of years, called The Same and Not the Same. And there's a lot of good stuff in this book, but there's a chapter on chemical mechanisms that's just brilliant. And this is his lead into the mechanisms chapter. So if it was good enough for Roald, it's certainly good enough for me. We're going to be talking about the mechanism of how reverse phase chromatography comes about. Now, I said one of the issues is it a partition process or is it an adsorption process? Partition process means it's an absorption process. When the guy eats the pie, he absorbs the pie into his body. That's a partition process. When he gets smacked in the face with a pie, that is a surface process. It is adsorption process. So when something winds up inside of something else, it's a partition or absorption process. If something winds up smeared on the surface of something else, like the top of that desk, it's an adsorption process. And the conclusion of this talk will be that reverse phase chromatography, insofar as the non-polar parts of a molecule are concerned, is a partition process. This was a very hotly debated issue. Once people realized how valuable reverse phase liquid chromatography was, they wanted to figure out how it worked. And there were many, many, many studies. So back to the driving force, the hydrophobicity question mark. Here's a quote from Ron Breslow. Breslow is no slouch. He was a former chairman of the American Chemical Society. He did a lot of work in organic chemistry where he thought he was using the hydrophobic effect to control mechanisms of organic reactions. And so in this paper, in Accounts of Chemical Research, he defined what he meant by the hydrophobic effect. And he says the hydrophobic effect is the principal force determining the structure of proteins and nucleic acids, the binding of substrates to enzymes, the binding of antigens to antibodies. It causes the formation of micelles and bilayers, in other words, cell membranes. in enzyme model systems operating in water, substrate binding into cyclodextrin cavities. That was one of his favorite hobby horses. And into other synthetic cavities is also driven by the hydrophobic effect. He makes it sound pretty important. In fact, if you read the whole paper, he says that the hydrophobic effect is in back of all of these things. He didn't list that, but that's clearly the most important application of the hydrophobic effect, at least in this classroom. So let's look at it by looking at some data. So is the transfer of a nonpolar substance from a nonpolar solvent into water a favorable or an unfavorable process?
Unfavorable?
Is the transfer of a nonpolar substance from a nonpolar solvent into water favorable or unfavorable?
Unfavorable.
In exactly what sense do you mean it's unfavorable?
The free energy is positive?
Thank you. The free energy is positive. It's an unfavorable free energy. That's what controls the equilibrium constant, right? Is the free energy. And if the equilibrium constant is really small, less than 1, it's unfavorable. The delta G will be a big positive number, unfavorable. Yes, it's unfavorable. How unfavorable? Very unfavorable. Okay, here's our solute. There, you can read the list. They're all very nonpolar substances: methane, ethane, benzene, toluene. The solvents here, there's a lot of solvents, but you have to say that these are all relatively, with the exception of ethanol, but I put ethanol in there just to show you how wide-ranging this is. Certainly all of these solvents are less polar than water, right? Even ethanol, although ethanol does dissolve nicely in water, but we're concerned with the transfer of methane from ethanol into water. And here are the delta G's, and these are kilojoules per mole. And they're all, except for the ethanol, they're all greater than 10 kilojoules per mole. They're rather unfavorable processes. These equilibrium constants would be considerably less than 1. Okay, so we agree that the transfer of a nonpolar from a nonpolar solvent into water is unfavorable. But why is it unfavorable? What are the components of delta G?
You have to break the bond of, you have to break up the interaction.
There are only 2 components of delta G. Screw the bonds. What are the components of delta G?
Enthalpy and entropy.
Huh?
Enthalpy and entropy.
Enthalpy and entropy. Remember, I told you entropy was always one of the 2 answers when you don't know what to say. Okay, let's look at the enthalpies of these processes. Is that a favorable enthalpy? Is it favorable? It's negative. Is a negative delta H favorable or unfavorable?
Favorable?
It's favorable. They're all favorable. That one's kind of neutral, and this one is slightly unfavorable. All of these delta H's are much less than the unfavorable delta G that they relate to. So why is delta G so unfavorable? It's got to be delta S. And I've written this as minus T delta S, not T delta S. And these are all rather unfavorable processes. So then, why is the transfer of a nonpolar substance from a nonpolar environment into water unfavorable? It's clearly not enthalpic. It doesn't have to do with the energies involved in the bonds that are broken or made or rearranged or reorganized. It's due to
Entropy?
the entropy. That is how the solvent is arranged around the solute molecule when it's in the nonpolar environment, and how the solvent water is arranged around the solute molecule when it's in the aqueous environment. And it's beginning to look a lot like, not Christmas, but the water system becomes more organized, meaning a lower entropic state, when the solute molecule moves into the water. And thus coming back out of water into the nonpolar environment is entropically driven. The reverse of what we're talking about is entropically driven. Here's the ratio of delta G to T delta S, and you can see that basically the delta G is tracking the delta S. As the unfavorableness of the entropy of entering water, which is what's responsible for the unfavorability of the solute leaving the nonpolar environment and going into the polar aqueous environment. Now, yes, Ryan?
Doesn't that mean at a very low temperature, enthalpy would dictate that it would prefer water?
Yep. If you assume that the water structure doesn't do something at that very low temperature. You're talking about very low temperatures because those entropies are really big, and you're going to have to make the T times the delta S become a small number so that the delta H, which is negative, takes over. So, and you're not going to have liquid water at those temperatures. So it's not worth pursuing that. Okay, now the processes I just showed you were kind of complicated processes, so I'm going to make it simpler. I'm going to look at this process, the transfer of xenon. There's not much which is less polar than xenon, except maybe helium. The free energy of the transfer from the state of a 1 molar gas into xenon dissolved in some solvent, also at a concentration of 1 molar. So we're actually evening out the translational entropy by making the 1 molar and the 1 molar standard state in both sides of the transfer. And let's look at these solvents, and you'll agree that these are all reasonably nonpolar solvents, including methanol, which certainly has a nice solubility in water, but it's a lot less polar than water. And the transfer from the gas phase into the solvent, not water, but into these nonpolar solvents, these are all pretty favorable transfers from the gas phase into the solvent. Another way to say that is if I made a stationary phase out of hexadecane and I injected xenon it would go into the hexadecane pretty willingly. Xenon, by the way, is about the same size as methane, but it's less polarizable than methane, so it's going to be less soluble than methane. But what about water? These are all favorable, but there's water. That's a big fat plus. So the transfer of xenon from the gas phase into any solvent that I've listed here, except water, is favorable. But the transfer into water is extremely unfavorable. This is kilojoules per mole again. No, not kilojoule, this is joules per mole. Here's delta H. And there's a shocker here. You should recognize it as a shocker. These are all, roughly speaking, about the same size. And they're all
Favorable.
favorable. And the water is almost twice as big, and it's favorable. Even more favorable than the enthalpy for the xenon to go into the organic phases. And that is predominantly the dipole of the water, the very large dipole moment of the water, polarizing the polarizability, inducing a dipole into the xenon. That makes it so enthalpically favorable. Now, if we look at the entropy, all of the entropies from the gas phase into the solvent are unfavorable. Well, you know, all of these liquids are going to impede the way the xenon can move around. And so the xenon's a lot freer in the gas phase than it is in a liter of water. 1 mole of xenon in the gas phase is really got more space to occupy than it has in a liter of these solvents. And these numbers are all, roughly speaking, about the same. But that's an exceedingly unfavorable entropy of transfer from the gas phase into water.